Alright, ladies and gentlemen, in this video we're going to talk a little bit more about empirical formula, getting empirical formula from combustion analysis problems. We did one of these problems together in class. I'm going to do two more on this video. I am stressing that the type of combustion analysis problem that we're doing here is not the most complicated type of combustion analysis, but it's the one that you're going to see. It's as complicated as it's going to get for us in here. So to remind you of what we were doing in this empirical formula from combustion information. First of all, the problem will always be asking you for the empirical formula of a compound, and it's really important to remember, like we discussed in class, that means that we are looking for the lowest mole ratio of elements in a compound. That's going to mean for us that we need to find a way to get moles. We need to have some method of getting moles, because once we get moles of every element that's in the compound, then we can figure out its empirical formula. So that's really the guiding principle. How is the information that's been supplied to us going to get us to moles of each element? As I've highlighted here, the key to the empirical formula from combustion analysis problem is this realization. Knowing that all the carbon, if we're dealing with a hydrocarbon, that we start with is turned into carbon dioxide, and all the hydrogen that we start with is turned into water. Making that connection, essentially a law of conservation of mass issue, that if we're ending with a certain amount of CO2, that carbon was not magically generated, that it came from the carbon in our empirical formula, in this unknown compound, and using then that carbon dioxide mass to essentially work backwards and go from the grams of CO2 to moles of CO2 to moles of C, and ditto for the water, saying that all the water, that hydrogen that's in the water, that didn't just magically appear, it came from this compound that we're being asked to investigate. And then, by working backwards, by using the mass of the CO2 to get moles of C and the mass of the H2O to get moles of H, you can then compare the masses to get the empirical formula. So, sample question. A 1.5 gram sample of a hydrocarbon undergoes complete combustion to produce 4.4 grams of CO2 and 2.7 grams of H2O. What is its empirical formula? I always think it's useful, always, to write out a rough reaction to describe what's going on so that we can essentially see what we're dealing with. This is combustion. It does say combustion in the problem, and it does say that it is completely combusted. That's going to be important for us because it means that we can make the assumption of going directly from the CO2 back to the C in the unknown compound. So CXHY plus O2 goes to CO2 and H2O, and we have 4.4 grams of carbon dioxide and 2.7 grams of water. Again, in the combustion analysis problem, key to solving it is the realization that all of this C becomes all of that C, and all of this H becomes all of that H. Because then, that right there will allow us to work with these numbers, to work backwards, to essentially figure out these values. So, getting started, let's take, again, automatic knee-jerk reaction. In AP chemistry, you see grams of something, you turn it into moles of that thing. So the carbon dioxide, 4.4 grams. The gram formula mass of carbon dioxide is 44. But we don't want moles of CO2, we actually want just moles of C. Again, we need the lowest mole ratio in this unknown hydrocarbon. So we need to then look at the subscripts and for carbon dioxide and say that for every 1 mole of carbon dioxide, we get 1 mole of carbon. That's coming directly from the subscripts. Because then we know that all of that carbon that's in that 4.4 grams of carbon dioxide, we've actually worked out how many moles of carbon we had to begin with on the reactant side. So doing this math out, we get 0.1 moles of carbon. Doing the same thing for the water. We're going to take the 2.7 grams of water, turn it into moles of water by dividing by the gram formula mass, which is 18. That gives us moles of water, but moles of water is actually a little insufficient. It's nice, but what we really want is moles of hydrogen because, again, we want the mole ratio between carbon and hydrogen in this unknown compound. So we've got the moles of carbon, we need the moles of hydrogen. So we're going to say for every 1 mole of water, there are 2 moles of hydrogen. And then we can do this math out. 2.7 divided by 18 and then multiplied by 2 gives us 0.3 moles of hydrogen. So we have 0.1 moles of carbon, 0.3 moles of hydrogen. Clearly this is a 1 to 3 for carbon to hydrogen. That should be very apparent by looking at those numbers. So the empirical formula for our unknown hydrocarbon is CH3. Looking at another example that's a bit more involved, because that was pretty similar to the one that we did in class. The known compound containing nitrogen and hydrogen was combusted, producing 31.3 grams of nitrogen dioxide and 12.4 grams of water. What is the empirical formula of this compound? Well, this is a little bit different because we didn't talk about nitrogen-containing compounds. We've been looking at hydrocarbons thus far. You know what it's going to mean because it's different for solving this problem? Nothing. We're going to do this exactly the same way. So we're not combusting a hydrocarbon anymore. So what? It says that the unknown compound contains nitrogen and hydrogen. All right, so let's write NXHY. Ooh, we're writing an N instead of a C. That's essentially the biggest change we've made so far. It's the only difference that's going to be making in this particular problem. We're still combusting it. We're still combusting it. That means adding oxygen. And it tells us what the products are. It says that the products are NO2 and H2O. Again, writing out a rough reaction to essentially describe what's going on. Filling in the numbers. 31.3 grams of this thing, NO2, and 12.4 grams of water. Again, key to solving this problem is realizing that there is only one nitrogen source on the left and only one nitrogen source on the right, which means that all of the N that's in this NXHY had to have turned into the nitrogen that's in NO2, and all of the hydrogen that's in NXHY had to turn into the hydrogen that's in H2O. That is the fundamental big point from this particular type of problem. It's law of conservation of mass. If we know moles of nitrogen and moles of hydrogen, we can answer the problem, and we're going to get moles of nitrogen from this number, from the NO2 number. This will eventually give us moles of N, and this 12.4 grams, that is going to eventually give us moles of H. So we're going to do the same thing that we did before. So what if it's with nitrogen and still the same type of problem? Doing the exact same stuff from previously. 31.3 grams of NO2. So you look up the gram formula mass of NO2, 46 grams for every 1 mole of NO2. We don't want NO2 as a compound. We are interested in the nitrogen that's in that specifically. So then we're going to look at the subscripts. For every 1 mole of NO2, there is 1 mole of N. That gives us moles of nitrogen. Doing that math out, we do have some decimals here. We're not getting numbers that are working out perfectly. 0.60804 moles of N. Same thing for the water. Problem gave us a couple masses. Okay, we'll do a couple T-charts with those masses. 12.4 grams of water, 18 grams H2O for every 1 mole of H2O. That gives us moles of water. We don't really want moles of water, though. We want moles of hydrogen because we are looking for the empirical formula of NXHY. That means that we need moles of N and we need moles of H. We already have the moles of N. This is getting us the moles of H. So doing out this math, 12.4 divided by 18 and then multiplied by 2, we get 0.1, sorry, not 0.1, 1.378 moles of hydrogen. Whether or not the ratio is clear to you right now, I think depends on how comfortable you feel with working with decimals. If you see the ratio, you can go right to the empirical formula. If not, you'll want to do this next step, wherein you find the smaller number of moles. You look at these two and you figure out which one is smaller. That's the nitrogen. So we're going to divide both of these values by the smaller number. That's how we get ratios. 0.6804. And obviously this, for the nitrogen, that works out to 1 N. And for the hydrogen, when we do this math, I think you get like 2.02 something, something, something. It's 2. It's approximately 2 for the hydrogen. And this right here is going to be our ratio, our empirical formula. 1 nitrogen, 2 hydrogens, it's NH2. That would be the empirical formula for this compound that we combusted. I do want to go back and make a note about the previous problem, because I didn't mention it when I was going over it. There's a 1.5 gram sample of the hydrocarbon. Please notice that we did not use that number anywhere in our calculations. That number, because we did not actually know the formula for the hydrocarbon, that number doesn't really do us much good. Instead, we're looking at the products because we know the formulas for the products. We know that it's CO2, 1 carbon, 2 oxygens. We know that it's H2O, 2 hydrogens, 1 oxygen. Because we know the formulas about the products, the masses for the products become far more important and far more instructive. That 1.5 grams doesn't really get us anywhere. We can't do anything with that because we don't have the formula for the hydrocarbon to begin with. We do, though, know much more about the CO2 and the H2O, so that's why we're working with those numbers, and actually not this 1.5 gram sample at all. I will add that if we combusted not a hydrocarbon, but a compound that contains carbon, hydrogen, and oxygen, which is a very common type of compound, then that mass of the hydrocarbon, the mass of the unknown compound would start to come into play, but that's not the type of problem that we have here. So it is actually an irrelevant piece of information, which is not uncommon on AP free response problems, for them to give you perhaps a little bit extra info that you don't actually need. Ha ha ha. Yes, they are trying to ruin your lives. Okay, so that is the empirical formula from combustion analysis information. I hope this is helpful when you are going over the homework.